discuss about the physical properties of aldehydes and ketones. In the physical properties, we have to discuss about the four important physical properties. Let us see what are those. The first one is physical state. The first one is physical state. Okay. Now, here we generally consider the three states of matter. One is gaseous state, the liquid state, and the solid state. The simple aldehydes. What are the simple aldehydes? The formaldehyde. It is a gas at room temperature. Formaldehyde is a gas at room temperature. See, we are talking about the physical state at room temperatures. So, at room temperature, formaldehyde is a gas. And the higher member of the aldehydes is the acetaldehyde. Acetaldehyde and a few more compounds are volatile liquids at room temperature. Okay. Usually the acetaldehyde is a volatile liquid. Okay. And if you take the third compound, that is propionaldehyde, is a liquid. Okay. Like that, butyraldehyde is a stable liquid at room temperature. Okay, means what you are understanding from this, as the number of carbon atoms in the chain increases, the surface area increases, boiling point increases. Okay, slightly it will become a gaseous compound to the liquid to the solid compound at room temperature. Okay, and further higher aldehydes. For example, the aldehyde with the 10 carbon atoms, that is decanol. Okay, that is decanol is a solid at room temperature. Means when you move from the formaldehyde to higher members, slightly there is a change in physical state from gaseous to the liquid to the solid. Okay, this is about the aldehydes. Then what about the ketones? The first member of the ketone is acetone. Okay, acetone is a volatile liquid at room temperature. See, the ketones start from 3 carbon atoms. Okay, therefore it is a liquid at room temperature, and higher members are stable liquids, and further higher members are solids at room temperature. So it is very simple, as the number of carbon atoms in the chain increases, that is in the homologous series, the higher members will take a transition from gaseous to liquid to the solid state. Okay. Next is about the odor. The second physical property is odor. Odor means smell. Okay. Generally, these aldehydes will have pungent odor. Pungent means unpleasant, irritating smell. Okay. The lower members of aldehydes will have pungent odor. As the number of carbon atom in the chain increases, that is moving from lower members to the higher members. Higher members of the aldehyde will have a less pungent or more fragrant smell, or we can say pleasant odor. The higher members of the aldehydes will have the pleasant odor. Okay. Here, due to this pleasant character, for example, benzaldehyde is used as a perfuming agent in the perfume bottles. Okay. Yes. What about the ketones? For example, acetone is having a pleasant odor. Ketones are having some pleasant odors. Okay, these are available in flowering plants. Okay, the aldehydes and ketones. Some of the aldehydes and ketones are extracted from the flowering plants, and these will give some odor. Okay. Yes. The third physical property is boiling point. Boiling point. See, about this, there is a common phenomenon that as the number of carbon atoms in the chain increases, surface area increases, van der Waals forces of attraction increases, finally the boiling point increases. Okay, means as the surface area increases, the boiling point increases. Okay, for example, I will write a common point as number of carbon atoms in the parent chain. In the parent chain increases, the surface area increases. Surface area increases. Surface area increases. And the van der Waals forces of attraction increases. Van der Waals forces of attraction increases. Okay. Then the boiling point also increases. Means these are directly proportional to each other. As the number of carbon atoms in the parent chain increases, its surface area increases, and van der Waals forces of attraction increases. Due to that, the boiling point of the compound increases. It is the same in case of aldehydes as well as in case of ketones. If branching increases, BP decreases, boiling point decreases. Okay, let us consider some examples here. Okay, so we know that the aldehydes or ketones are polar in nature. Means there will be a dipole, that is a delta plus and delta minus. It will attract the other molecules. Okay, these aldehydes and ketones cannot make hydrogen bonding, therefore whose boiling point will be lesser than that of alcohols and carboxylic acids. And the boiling point of these aldehydes will be higher than the corresponding ethers and the hydrocarbons. Let us see that. Okay. Order of BP. For example, we take a compound, some kind of compounds with 4 carbon atoms. In the case of carboxylic acid, we will have a butanoic acid. Okay, that is CH3, CH2, CH2, COOH. What is this? Butanoic acid. It is a kind of carboxylic acid. It is a carboxylic acid. Okay. Whose BP will be higher when compared to the butanol. That is corresponding alcohol. That is CH3, CH2, 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 OH. This is an alcohol. Okay. Whose BP is higher than that of the butanol, that is a aldehyde. For example, CH3, CH2, CH2, CH2. This is an aldehyde. Okay. Whose BP is higher than a corresponding ketone, that is CH3, CO, CH2, CH3. This is a ketone. Okay. And here the BP of these ketones is higher when compared to the ethers, that is CH3, CH2, CHO, CH2O, CH3. That is ketone. Whose BP will be definitely higher than the hydrocarbon, that is butane. CH3, CH2, CH2, CH3. Okay, this is a hydrocarbon. Okay, here why the BP of these carboxylic acids is high when compared to all these? Because it is undergoing association and it also makes the hydrogen bonding, intermolecular hydrogen bonding. It undergo association means the carboxylic acid molecules will come nearer and nearer and will be having strong forces of attraction. To break that bond, we need to provide high thermal energy. Therefore, to boil the carboxylic acid, it requires more thermal energy, means it will have a higher BP. Okay. Here, what is the reason for the high BP of the carboxylic acid? The molecules are undergoing association because of presence of intermolecular hydrogen bonding. Intermolecular hydrogen bonding. Okay. And why the BP of alcohol is less than carboxylic acid or greater than the aldehyde? Because it is having only the intermolecular hydrogen bonding. It is having only the intermolecular hydrogen bonding and it cannot undergo the association. Okay. Why the BP of this aldehyde is less than this? Because it's a polar molecule. Okay. It is just a polar. It is a polar and also makes the intermolecular hydrogen bonding. Okay. And come to this. This is a weakly polar molecule. Weakly polar. That is why attractions are less. Okay. Therefore, whose BP is less than the aldehyde. Okay. Come to the ether. It is a very weak polar compound. Very weak polar. Okay. And come to the butane. There is no forces of attraction. No forces of attraction except van der Waals forces. Okay. So here it is a non-polar. Okay. Yes, in every these compounds there will be a van der Waals forces of attraction. What is the van der Waals forces of attraction? It exists between any kind of molecule. It is just a weak force of attraction. The weak force of attraction is called as a van der Waals force of attraction. Okay. So this is the reason the carboxylic acids are having higher boiling point. Let us see the BP in case of isomers. Let us discuss about the order of boiling points in case of isomers. This is a common fact that as branching increases, boiling point decreases. Okay, let us see that in case of a butyraldehyde, in case of a butyraldehyde or butanol. Okay, that is in case of butanol. In case of butanol. Okay, let's see that CH3, CH2, CH2, CHO. It is a normal butanol. It is a normal butanol or normal butyraldehyde. Okay. In common system, we usually call this as a normal butyraldehyde, or in the IUPAC system, we can call it as 1-butanol. Okay. Now, if you take the branch in this, okay, what happens? CH3, CH, CH3, CHO. Okay. These two are isomers. What kind of isomerism is there in between these two compounds? The chain isomerism means two compounds having same molecular formula but differ in the number of carbon atoms in the parent chain. Here there are 4 carbon atoms. Here only 3 carbon atoms in the parent chain. Okay. So now the BP of this 1-butanol is high because it has a higher surface area, greater surface area than this. Okay. And what is the name of this compound? It is a 2-methyl propanol. It is a 2-methyl propanol. 2-methyl propanol. Okay. Yes. So this is the simple discussion about the variation of boiling point in isomeric aldehydes. As branching increases, boiling point decreases. Okay. And in case of homologous series, when you move from the formaldehyde to acetaldehyde, acetaldehyde to propionaldehyde, then to butyraldehyde, as the number of carbon atoms in the parent chain increases, the boiling point increases. It is already discussed. Okay, we shall discuss about the fourth physical property, that is solubility. That is solvent. See, there is a common fact that the organic compounds are generally soluble in organic solvents. For example, the aldehydes, ketones are readily soluble in organic solvents like benzene, ether, alcohol, etc. Okay. So the first statement is organic compounds. What we are discussing about? We are discussing about the aldehydes and ketones. We are discussing about aldehydes and ketones. These are organic compounds. Okay. These are soluble in the organic solvents. Soluble in organic solvents. So what are organic solvents here? You may take benzene, okay, ether, alcohol, carbon disulfide, etc. Okay, these are soluble in benzene, ether, then chloroform, alcohol, etc. Alcohol, etc. Means organic compounds are generally soluble in the organic solvents. Okay, then what about the solubility of these compounds in water? Okay, let us see. That is case B. In water, see, any compound to be soluble in the water, it has to match the property of the water. What is the property of the water? It is a polar. Okay, it is a polar and makes hydrogen bonding. Okay, if any compound satisfies these two conditions, then it is readily soluble in the water. Okay, for example, the formaldehyde, acetaldehyde, acetone are polar and make hydrogen bonding with the water and make hydrogen bonding with the water and make hydrogen bonding with the water. Therefore, these are soluble in 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 water. How the aldehydes or ketones are going to make hydrogen bonding with the water? Let us see that. Okay. For example, I have a C double bond O like this. It may be an aldehyde or a ketone, and take the water here H2O. For example, like this, we are going to take the H2O, then C double bond. Okay. Here you know that the carbonyl group is a polar one, delta minus, delta plus. The hydrogen, that is water, is a polar one where the hydrogen is delta plus. Why it is delta plus? Because the electronegative oxygen is pulling electrons towards itself, no? Towards itself. So it is rich in electrons, it is deficient in electrons because it is losing electrons towards the oxygen. Okay, so it is delta plus, again delta minus. Okay. And here this is delta minus, and between the carbon and oxygen is more electronegative, pulling electron towards oxygen, no? And this carbon is delta plus. Okay, here delta plus and delta minus are near to each other and will are having opposite charges and will attract each other. Okay, yes. This attractive force is intermolecular hydrogen bonding. This attractive force is intermolecular hydrogen bonding. Okay, and here also intermolecular hydrogen bonding. See, when we call the attractive force as hydrogen bonding, we need to understand the definition of the hydrogen bonding. It is a force of attraction between the hydrogen and most electronegative elements. It is the force of attraction between the hydrogen and the most electronegative element like fluorine, oxygen or nitrogen. Okay. Only these three elements. What are the elements? Fluorine, oxygen, nitrogen. Only these three elements can make a hydrogen bonding with the hydrogen. Okay. But not with chlorine, bromine or any others. Okay. Yes. This is all about the solubility of the aldehydes and ketones. Aldehydes, the lower members, okay, the lower members such as formaldehyde, acetaldehyde in case of aldehydes, and in case of ketones, the acetone is soluble in water because these are sufficiently polar and make hydrogen bonding with the water. Therefore, these are soluble in water. When you go for propionaldehyde, butyraldehyde, pentanaldehyde, these are having a less polarity and the hydrocarbon part is more. It is the hydrocarbon part is having hydrophobic nature. Okay, and it will reduce the polarity or mask the polarity of the molecule. Therefore, those higher members are insoluble in the water. Higher members are insoluble in water. Higher members, okay, are insoluble in water. Are insoluble in water. Okay. So this is all about the physical properties of the aldehydes and ketones. Let us discuss about the chemical properties of aldehydes and ketones. Here, the aldehydes and ketones are having a very similar properties. Okay, that is why we need to discuss about these two together. This aldehyde and ketone are undergoing similar type of the reactions. The difference between the aldehyde and ketone is only this much. When you look at the general reaction, general formula of the aldehyde, this is that RCHO and RCOR. What is the difference? Here there is a hydrogen, here there is a alkyl or alkyl. Okay, that is only the difference. The chemical property of the aldehyde or ketone is majorly decided by the carbonyl group. That is why the chemical properties of these two compounds are similar. Okay. Here we need to discuss about the first one is nucleophilic addition reaction. Nucleophilic addition reaction. Okay. Then reduction reactions. Okay. Then the oxidation of these compounds, and the fourth one is reactions due to presence of alpha hydrogen, reactions due to no alpha hydrogen. Okay. Then the sixth one is electrophilic substitution reaction. Electrophilic substitution reactions. Here we need to discuss about the six types of reactions. Number one is nucleophilic addition reaction. Second one is reduction of the aldehydes and ketones. Third is oxidation. The fourth one is reaction due to presence of alpha hydrogen. The fifth one is reactions due to absence of alpha hydrogen. The sixth one is electrophilic substitution reactions. We shall go one by one. Firstly, we shall discuss about the nucleophilic addition reactions. Yes. Nucleophilic addition reactions. Why the aldehydes and ketones are undergoing nucleophilic addition reaction. Let us understand that. Okay. Take the carbonyl group. Okay. Here oxygen is more electronegative. Okay. Therefore it is delta minus. It will pull the pi electrons towards itself, and the carbon will lose the electrons. So therefore it is delta minus. Now it is electrophilic in character. It has electrophilic nature. The carbon is having the electron deficiency or electrophilic character. The nucleophile will attack on this carbonyl carbon. The nucleophile will attack on the carbonyl carbon. That is why it is called as the nucleophilic addition reaction. Because this carbon is electron deficient, the nucleophile is going to attack. Because of that reason, it is termed as nucleophilic addition reaction. We are concentrating on the nature of the carbon atom, but not the nature of the oxygen. Okay. In general, the reactions are named based on the carbon atoms. Okay. Yes. Here, firstly, we shall consider a general mechanism for the nucleophilic addition reactions. In the examination also, they ask you to explain the nucleophilic addition reaction of the carbonyl compounds. Then you have to write this. Okay. Let us consider a general reaction mechanism. General mechanism of nucleophilic addition. Okay, let us take the carbonyl group. Okay, this is the carbonyl compound. This is the carbonyl compound. What is the shape of this? Because this carbon is sp2 hybridized, no? Because this carbon is sp2 hybridized, it is having trigonal planar geometry. Trigonal planar, or simply we can write planar geometry. Okay. Yes, when nucleophile is coming towards this, here we have a delta plus, it is a delta minus. Here it will attack. Okay, simultaneously this pi bond will jump onto the oxygen. The pi bond will jump onto the oxygen. Okay. Now what happens? A reversible slow step reaction takes place. Okay, this is a slow step, and it is a reversible step. Okay, this is called as step 1. It is a step 1 is a slow and reversible. Okay, and now the geometry will be changed to nucleophile is attacked. Now these two bonds will adjust themselves like this. Okay, then O minus is there like this. It is a intermediate and unstable. Okay, when this is treated with the electrophile. See, in the reagents there will be two parts, negative part and the positive part. Here negative part is attacked, no? Now the positive part will attack. It will be usually a proton. Okay, that is a H plus ion. This is a step 2. Sometimes this can also be reversed. Okay, yes. Where it will attack on the O minus, therefore we have Nu, that is nucleophile, OH, then a bond, then another bond. Okay. So now, what is the hybridization of this carbon? This carbon is sp3 hybridized. How can you say that? When a carbon is surrounded by 4 sigma bonds, that is 4 sigma can be written as S1P3. Here 1 plus 3 is equal to 4. When a carbon atom is surrounded by 4 carbon atoms, then the carbon will be in the sp3 hybridization and the geometry will be tetrahedral. and the geometry will be tetrahedral. Okay. So what you are understanding from this mechanism here, a carbonyl compound, maybe an aldehyde or a ketone, when treated with the reagent, the nucleophile will attack on the electrophilic carbon. Okay. Yes. Then it will change its geometry from trigonal planar to the tetrahedral because of the change in the hybridization of the carbon. In the first step, only the nucleophile will attack. It is a slow, reversible step. Okay. In the second step, the positive part of the reagent will attack and give you a stable product. Okay. This is a general reaction mechanism. Let us discuss about the reactivity. Means whether the aldehydes readily undergo this mechanism or ketones will readily undergo. Let us discuss about that. Okay. Reactivity. Here I will give you a statement, that is, aldehydes readily undergo the nucleophilic addition reactions than the ketones. Why? Let us discuss about that. Aldehydes readily undergo nucleophilic addition reactions than ketones because so what is the statement here? The aldehydes readily undergo nucleophilic addition reactions than ketones because of two reasons. Okay, what are the two reasons? The first reason is steric hindrance. What is steric hindrance? Stereo means space. Hindrance means restricting. Okay. See, if you come late to the classroom, what we do as a lecturer, we tell you to stand outside for 2 minutes or 5 minutes. Means it is like giving a punishment. Okay. And then we will take you in. Similarly, like that only, if the steric hindrance is more, already the classroom is full. Okay. Some extra people have to stand outside, like that. If already the bulkier group are present, then the nucleophile has to wait. Let us see what happens in case of these aldehydes and ketones. Okay. The first reason is steric hindrance. Let us observe the general formulas of the aldehydes and ketones. What is this? This is an aldehyde. Okay. What is this? This is a ketone. Now, nucleophile is coming to attack on these carbonyl carbons. If nucleophile is coming towards this aldehyde, how it will attack? It will attack from this end. Because here there is oxygen now. It has to attack from this end. Okay, now what happens? Here there is a one bulky group. What is this? A bulky group. Means whose size is heavy. It may be alkyl or aryl group. Okay. Now there will be repulsive forces between this bulky group and the nucleophile because both will be having the electrons. No? So this bulky group is objecting nucleophile to get attacked to the carbonyl carbon. And here we have hydrogen. It won't restrict the incoming nucleophile because it is having only one electron. So it won't restrict. Okay. Come to this point. If nucleophile is coming to attack on the carbonyl carbon, here there are two bulky groups. Two bulky groups are there in ketone. This will definitely repel the nucleophile to greater extent. Okay, therefore nucleophile attack on the carbonyl carbon will takes place slowly. Okay, because of the steric hindrance is more due to presence of two bulky groups. Here only one bulky group, the hindrance is less, therefore it will readily attack on this. Okay, in this case aldehyde steric hindrance is less, reactivity is more. Here steric hindrance is more, reactivity is less. Okay, steric hindrance, here we can say that the reactivity is inversely proportional to steric hindrance. Reactivity, that is a nucleophilic addition. Okay, reactivity, nucleophilic addition is inversely proportional to the steric hindrance. Steric hindrance. If hindrance is more, reactivity will be less. Okay. Here, which one will readily undergo the nucleophilic addition reactions? The aldehydes. Okay. We can say that aldehydes readily undergo nucleophilic addition reactions because steric hindrance is high in ketones. Steric hindrance is high in ketones. Okay. Then, what is the next one? The electronic effect. The electronic effect or electronic reason. What is that? Okay. When you take the general formulas of the aldehydes and ketones, here there is an electron donating group. There is an electron donating group. Okay. It will donate the electrons towards carbonyl carbon. Okay. Coming to here. Here there are two electron donating groups. There are two electron donating groups. Particularly, it is called as the inductive effect. Okay, displacement of sigma electrons towards the carbonyl carbon. Okay. See here, when a nucleophile come and attack on this carbon, this is sufficiently electrophilic in character. This is less electrophilic in character. Okay, this is electrophilic in character. No, that is why it is readily attacked by the nucleophile. It is highly electrophilic in character. The carbonyl carbon in aldehydes, the carbonyl carbon. Here I can write that statement: carbonyl carbon in aldehydes is electrophile. Then readily attacked by the nucleophile. Readily attacked by the nucleophile. Okay. While the carbonyl ketones is less electrophile, slowly attacked by the nucleophile. Okay. Here positive character is more, that is why it is readily attacked by the negative nucleophile. Here positive character is less, that is why it is slowly attacked by the nucleophile. Okay. Where the steric hindrance is more in ketones, where the positive character is less here in ketone, that is why it is not readily attacked by the nucleophile. So this is all about the reactivity of aldehydes and ketones towards nucleophilic addition reactions. This is a very important point asked many times in the examinations. The question will be like this: aldehydes readily undergo the nucleophilic addition reactions than ketones. Give reasons. The first reason is steric hindrance. Steric hindrance is more in ketones, therefore it is slowly undergo reaction. Steric hindrance is less in aldehydes, that is why it is readily undergoing the nucleophilic addition reaction. This is the first reason. Second reason is the electronic effect or inductive effect is less in aldehyde. Okay, Electrophilicity of the carbon in aldehyde is high, therefore it is readily undergoing the nucleophilic addition reactions. Okay, you need to focus on these a lot.